掉了。
啊？什么？
倒水倒洒水倒吧。等了一半了。
三 D 方。
我先比一下。
Hello，OK。啊？
我们 still relation
啊？
relation 怎样 generate 3个
把它看成 Word
现在我会给我 identity
啊？
会给我 identity
哦，没有啊，我在，我等下可以解释一下。
挖代，那叫挖代。
哇，三 D 方。人家是我老师会传这样。
你确定你老师参加？
我老师真的专家，真的，好少笑。
都没有钱。
还有 extend open 然后不是啊？那你一辈子忘不了他。
看到这种比较有人去的group 是啊。
Oh, okay, let's start. Right, so we will play more on group presentation by generators and relation before we go into group action. Okay, so what's this notation means? Anyone can recall? What does it mean? This is a group generated by G and H. So the first half of this notation is called generators. Satisfying some relation. Okay, satisfying some relation. So what's relations? Relation is a word. Okay, relation is a word. So what's the usefulness of this word? So this word says that how G compose, how the generators compose with each other. Okay. So in this case, when you see this number, see this word, you will get identity. Okay, so very good question. Adrian asked, if all of these equals to identity, well, right. So there's another description, right? I said that this is a, let me write down first. So this is a free group quotient by the normal subgroup. So let's put the normal subgroup here. Generated by this word. Okay, generated by this word. Okay, generated by this word. So I put N here, normal subgroup. Not just a usual subgroup, it's a normal subgroup. So normal subgroup generated by this word means what? First of all, it must generate as a subgroup. Second of all, it must be normal. Normal means what, Albert? Forget. Okay, go and check. 金鱼. What does a normal subgroup means? I don't know. Hey, 你的 midterm 考得挺高的。哎，还行。Ian 呢？ GH inverse is living in H. So if you take any group element conjugate with all these words, it will live inside the normal subgroup that you generate here. Okay? But agents say that since we take this word to be identity, isn't it? If you generate with identity, you just get identity. So what does it mean by I put equals to E here? Okay, so there are two. I mean, why is it equal to E? Because it is after we taking the quotient of these words. And we take quotient of these words, meaning correct or not? What's the E here means? Remember how we define free group? We use equivalent class, right? To define free group. So meaning after quotient by this word here, what's left inside this group here? What's left? For example, okay. So let me write down something here. So inside here, G is equals to what? G is equals to G times GH, G inverse, H inverse, for example. Okay. Okay, no. This is what it means by GH, G inverse, H inverse is identity. Okay, because it's under this quotient here. So because this is a quotient group, right? Quotient group is a set of coset. Okay, so in principle, I should write G bar and G of this whole bar here. Okay or not? Does it make sense? For example, I mean, go to some very small example that we do last time. So for example, if you put Z mod 3Z, right? Okay, inside here, what is the same with what? For example, 2 is same with 2 plus 3 bar. Correct or not? You are adding something from the subgroup that you quotient by. Okay, so I'm adding something from the subgroup that I quotient by. Okay or not? Okay, so whenever we say equal E here, we are already talking about quotient group already. Okay, when we put equals E here, we are talking about what we do to this coset. Okay, but like what I told you last time, right? We understand that we live in the coset world, so we just disregard coset. Okay, I mean disregard the notation. Okay, no. But in principle, we are working in a coset setting because it's a quotient group. Okay, so by definition, if you can write down this group presentation, if and only if you have this isomorphism, or because it's a definition, we just say if. Okay, if your group is isomorphic to a free group quotient by a normal subgroup generated by the word. Okay, no? Does it make sense? Okay, so in principle, relation is a word. Okay, but why is it equal to identity? Because we consider it as a quotient group. Okay, quotient by these words. Does that make sense? Okay. So let me ask you a question. If I send these elements to identity, where do I send the conjugate of these words to? Also identity, you know why? So let me write down something here. So if I have, let's say, M, G, H, G inverse, H inverse, M inverse. So inside here, this is equals to what? This is equal to M of identity M inverse. And then M and M inverse will cancel also. Okay, so that's why we pick to quotient by a normal subgroup. Okay. Okay, because if you send one thing to identity, the conjugation will also go to identity also. Okay, because the starting and the end will meet again if you send the middle thing to identity. Okay. Okay, so that's why we care about this normal subgroup here. That's why we quotient by normal subgroup. It's natural that these conjugate elements will go to identity also. Okay, if the element you conjugated with is already live in the identity coset here. Okay, actually it's coset. So I mean, I don't want to every time put coset here, but you need to remember we are working in the coset setting. Okay. Whenever you see these quotient group, you are always living in coset setting. Okay. But to save, for convenience, we just remove the bar. Okay. Okay. Any question? Okay, if no question, but I still want to deal with this example first. So actually, I claim that there are some redundant relation inside this presentation. Let me copy it. Okay, redundant means some of the word is already implied by the other word. Okay, so let's see how I play around with this relation here. Well, okay, so what can you see here? What can I see here? Let's see. Okay, so what can you see inside these three relation here? There's one commutator here. Okay, if the commutator exists as a relation means what? All the elements will commute. Ask you to prove in your exam, right? Okay, so if you send all the commutator to identity, then this group will commute. Okay, so meaning what? Meaning you can rearrange one of the word. For example, which word? For example, this word here. Okay, you can commute. So meaning what? You can put G to the one side and then put hash to the other side. Okay or not? Okay, but what's the good things about doing this? We can cancel out, can do some cancellation. Okay, then after cancelling, what we left is this new word here. Or we left with G hash and G hash. Okay, so meaning what? Meaning what we ended here is the same relation what we started before. Okay, so think about it. If I send G hash to identity, am I sending that G hash G inverse hash inverse to identity? Okay, so let's check. So if we know that this goes to identity, this part here will go to identity first, right? And this part will go to identity, and then G hash go to identity also. And then how about the rest? How about the rest? Is it going to identity? Huh? Is it going to identity or not? 没错，像那个青蛙一样，很努力的睁开眼睛。So, what do we left here? Is this identity or not? If we know that GH goes to identity. GH go to identity implies what? H inverse, G inverse also go to identity, right? Cancellation law. So this part go to identity, and hash inverse will cancel eventually. So the bottom relation will imply the top relation. Okay, but how the top relation imply the bottom relation? is how I computed. Then I need to use extra condition here to compute. Okay. So can we go further simplification or not? Can we simplify further? Okay, if I know G hash go to identity, can I simplify the other word or not? How? Which one can we simplify, for example? Hmm? You see? Which word can we simplify now? Which one? First one. Okay, first one can reduce to what? Immediately reduce to identity. Okay, maybe we can just cancel it out. Okay, last one. Can we simplify the last one further? Left what? GG. GG again. Is GG sound familiar to you or not? Exam question. So G is order 2, meaning G is X inverse. Okay, G is X inverse. Okay. Can we? Yeah. Okay. So let's stop until here first. Well, since you have G equals to H. Okay. So so G is equals to H. Sorry. G hex is equals to identity, meaning what? G is equals to H inverse. Okay. Or in other words is what? H equals to G inverse. But G inverse is just G. Oh. So actually these two generator is the same. Okay, so we can throw away one of the generators. Can you recognize what group is this? You have one generator, and then that generator is order 2. Sorry? Transposition, subgroup generated by transposition, which is isomorphic to Z2. Okay, isomorphic to Z2. So what's the isomorphism here? You send G to 1. Okay, inside Z2. Okay, no? So Z2 got 2 elements. G here also got 2 elements. What's the 2 element inside here? A group generated by G with order 2. What is the element inside here? G and E. G squared equal to E. Yeah. So 2 things inside Z2 also, right? 0 and 0 and 1, correct. So the identity should go to 0. So this is the isomorphism. Okay, so in principle, you can play around with these words. Any question so far? Yeah, relation. So if you're given a bunch of generators, given a bunch of relation, you can try and simplify whether you can reduce your relation or reduce your generators or not. Okay, how about the other one? I want to show you another technique of proving using free group. So let's take a free group generated by 2 elements. So I put A2 here, XY. Anyone can recall what's a free group generated by 2 elements? You just multiply XY anywhere you want. Okay, anywhere you want. Now, my claim is I'm going to build a surjective homomorphism to S3. Okay, what's inside S3 here? 1, 2, 1, 3, 2, 3, 1, 2, 3, 1, 3, 2. Good. So 6 of them. 3 factorial, right? Okay. So what's the map I'm gonna map here? So by mapping property of free group, what we need to define was I just need to tell you where the generators go. Okay, I just need to tell you where the generators go. So I'm gonna pick a specific one. Don't ask me why I pick. Later you will see why I pick like this. Okay. So X, I'm gonna send it to, for example, 1, 2, and then Y, I'm gonna send it to 1, 3, 2. So my claim is I just tell you where the generators go. I have a homomorphism now. Then I can extend it. Can extend it uniquely. Okay, this is the mapping property of free group. Okay. Why? Because a homomorphism need to satisfy what? Phi AB equals to phi A times phi B. Okay. But if I know that this group, okay, this S3 here can generate by these two elements, then I just I just send the generators on the left to the generator on the right. Then I can make a surjective homomorphism. Okay, I can make a surjective homomorphism here. Can you see that 1, 2, and 1, 3, 2 generates the group? Can or not? Well, I mean, we can certainly generate identity map 1, 2, and 1, 3, 2. How to get 1, 3, 2, 3, and 1, 2, 3? Using 1, 2, and 1, 3, 2. Maybe do a little exercise here. 1, 3 equals to what? 1, 3 equals to what? Can quickly do some calculation. So maybe I teach you some technique here. So 1, 3 is a odd permutation, right? Okay. So 1, 3, 2 is a even permutation. Okay. So well, you need to get an odd permutation, meaning what? You need to somehow add even and odd together. Multiply some odd and even together. Okay. So what's the possible product here to get 1, 3? 1, 2 times 1, 3, 2. Good. 对吗？对呀 okay. Checking, just checking. Okay, how about 2, 3? 1, 3, 2. 1, 2, good. How about 1, 2, 3? 1, 2, 3 is just the inverse of 1, 3, 2. Okay, so actually you can generate S3 using these two elements. Okay, so actually this is a surjective homomorphism. Okay. Can see or not? Okay. How about I demonstrate one of them for you? For example, if 1, 2, 3, yeah, maybe try the other. 2, 3 is equal to 1, 3, 2, 1, 2. So who gonna send here? You're gonna take y times x. Okay, because phi y times x equals to phi y times x. But I tell you where I send y and x to already. Okay, exactly 1, 3, 2 times 1, 2. So it is 2, 3. Okay, so you can check for all of them. Find their pre-image. Okay. Right. So what's my goal here? My goal here is I'm gonna show this. So my goal here is I'm gonna show this, or I'm gonna show that. I'm gonna show that there's a isomorphism between F2 quotient by these okay, let's not write like this. So just xy and then take the relation x squared dot y cubed dot yx or x. Okay. So first part here, we build using mapping property of free group. The second part here, we're gonna find this isomorphism. Okay, so how should we do it? We'll use mapping property of quotient group. Quotient. Okay, so how are we gonna find this? Well, I mean, so there's a canonical map here. Okay, so what's this canonical map here? We just send every element in F2 to X representative. Okay, sorry, the other way around. We send the representative to X coset. Okay, to a coset. So remember what this group says. This is a group. Okay, so remind you again. This is a group generated by, what's the generator here? S and Y. Okay. By the normal subgroup generated by the word. Okay, generated by the relations. Okay, so there are three relations here. Right. So let's call this normal subgroup some name. Let's call it X. X. Okay. So when does this map exist? What did I told you last lecture here? So you need to check that this X, okay, this X will live inside the kernel of phi. Okay, this X should live inside the kernel of phi. Okay. So well, I mean, if X is equal to kernel of phi, this is just the first isomorphism theorem. Okay. But mapping property of quotient group is more general than first isomorphism theorem. You can consider something smaller than the kernel of phi. Okay. If you consider something smaller than kernel of phi, what you get is a map from this quotient group to S3. Okay. Might not be isomorphism, but there is a map such that this diagram will commute. Okay. What's the map here should be? What's the map here should be? What should the map here be? It's the same one. Because if you want to make this diagram commute, you know that A should go to phi A. So this map should be just sending AN to phi A because you need to map this diagram commute. Do you still remember what does it mean by diagram commuting? So you have one starting point, right? You have one destination. But you have two ways to go around it. Then this two way have to be the same. Okay, so pretty much the first root already decide what this AN should go. Okay, you have no other choice actually. No choice. Okay, if you want to make this diagram. So you really have to send this AN coset to where A have to go. Understand? So what's the difference between the first map here and this last map here? 一样的终点，不一样的起点。起点怎么不一样？ One is element, one is the coset that contains the element. Okay. Okay. So I mean, what's the difference here? Here we talk about separate different elements inside the group, but here we group all what? We group all the elements that get sent to the same place. Coset, right? We group all the elements that have the same image together first. Okay, so this is the difference between sending AN and A. Okay 了。这边有很多东西哦，知道吗？这边是个 coset。OK， 这里有很多东西。这么多东西跟 A 是什么共通性？它们都有一样的 image under phi， 是吗 ？phi AN is what? Phi A times phi N。But N 是什么 ？N 是一个东西活在 A， 取太多名字了哦，不要 S 取回它的 N。AN is something living inside the kernel. Okay, so phi N is identity. So here actually I group everything that's sent to the same place together. Okay, right. So can we check that these words actually live inside the kernel? So I claim that to check that normal subgroup generated by this word is living in the kernel, I just need to check the generators. Because once we know that these are living in the kernel, the conjugation also live in the kernel. Correct? Not just now we do the computation. If the middle thing go to identity, G and G inverse will cancel later. Okay, so we just need to check this. It's in the kernel. Okay, if we want to check this one, is live in the kernel, how to check? So you need to check whether phi x squared, phi y cubed, phi of yx is in the kernel or not. Okay, is it in the kernel or not? So just quickly compute it. Okay, so what are these? We send x to 1, 2. We send y to 1, 3, 2. We send 什么 1, 3, 2啊？什么东西全部不见了 ？GG。哇，糟糕，怎么办？啊，关掉看。对 ，and score。Okay, so 全部人算下是不是去到 identity？Try check. Is it going to identity? Check yourself. Is it going to identity? Okay. Okay, so once you check the relation, and then the conjugation will also send to the identity. Also, the product of them will send to the identity. Inverse also send to identity. Okay. Okay, good. Well, so okay, so mapping property will give you a map. Okay, so there exists a map. So there exists a map called say phi bar. Okay, from this presentation to S3. Okay, but we still have isomorphism to deal with here. Because we don't know the kernel of phi whether it's equal to n or not. If you can show that the kernel of phi is equal to n, then you can use first isomorphism theorem. If not, that's another way to go around. Okay, how to go around with it? First, you compute how many elements on the left and right. Okay, because if you need isomorphism, you need a bijection. So they have to have the same number of things. Okay, so on the right hand side here, you know there are 6 things here. Do you have 6 things here? Okay, if you have more or less, you cannot be isomorphic already. So how many things inside here? How many things? How many coset inside here? In other words, how many coset inside here? So from the term x squared, can you see how many coset related to x or not? So first, surely you have a identity coset. Okay, let's call it n. And then Sn, right? Okay, S is not cubed. Only S squared is get cubed. What else? Y, n, y square n. Anything else? Sorry, want to try? Xyn, and then xy square n. Anyone want to try? Why not? Why not? 哪里来的？这6个？子涵，还有吗？中文没有？为什么没有？你不知道？不然你再说一个嘛？你觉得应该要有的东西？哎呦，道教从猜开始。数学东西，数学有一个东西啊，叫做猜想 （conjecture）。你一定要猜想。If you're not gonna guess, you're not gonna learn. Okay, you cannot just accept what people say. You must guess and then test your theory. Right or wrong? Ty? Right, I said yx. Yx? Đây yx à? Yx bao giờ? Okay, do yx. Okay. So, my claim is the previous 6, okay, they are distinct concepts. Okay. So why is this the extra one? Okay, so I will prove to you why is this the extra one. Okay, so how to see this is an extra one? Right? So last relation here will comes in handy. Okay, because the last relation here tells you how y and x react with each other. Okay, so from the last relation here, what do you get? Yx equals to identity. Meaning what? Yx equals to what? X inverse and y inverse. But what is x inverse here? X is the order 2 element, so it will be x inverse. What's the inverse of y? Y squared, because order 3, right? Y times y squared is identity. So y squared is the thing that multiply to y to be identity. You can do both way. So meaning what? Yx coset here is equal to x y squared and coset. Okay, so these two coset is actually the same. Yeah. Okay, so I mean, I have go through one review, right? So what did I say last time? So if you look at this relation here, this will tell you how to commute y and x. Okay, but when you commute y and x, it has the expense of adding one extra y here. Okay, so in principle, if you look at all the coset here, right, all the representatives, you can write x on the left side, y on the other side. And then you use x squared and y cubed to reduce all the power. Okay, reduce all the power until you're left with these distinct concepts. Okay, so there are 6 of them. And then where is the image of 6 of them? What's the image under phi here? What's the image under phi? What's the image of n under phi? Identity, right? X then? Sn 5x, which is 1, 2. And then 5y, 1, 3, 2, y squared, 1, 2, 3. Okay. Xy, 1, 2 times 1, 3, 2. What do you get? 1, 3, and then 2, 3, and then finish. Okay, so that gets sense to different level. I'll write down a full argument inside the lecture note so you can follow. Any question? Okay, so the key takeaway here is if you know that your n is equal to kernel of phi, you can use first isomorphism theorem. If not, you need to check whether the homomorphism is the isomorphism. Okay, you need to check yourself. Okay, because mapping property of portion group just give you a homomorphism to play. Just homomorphism. Commuting homomorphism, not isomorphism. Okay, if you want isomorphism, you need to show that n equals to kernel of phi. Okay, any questions so far? This example is kind of important for your next assignment, coming out assignment. Okay. Any question? No. Okay. Right. Okay, so we're gonna go to fun stuff now, which is called a group action. Actually, group action, the idea of group action comes earlier than group itself. Okay, group action. This is a really very realistic stuff. So let's see why is it realistic. So let's motivate again. So one of them is called the symmetry of triangle. I've mentioned it when we want to introduce group. Okay, so what's the symmetry of triangle here? Actually, it's actually S3. So let's call it X3 now. So where's the three things you're gonna permute here? Actually, we can permute the vertexes. Okay, so let's name this vertex 1, 2, 3. Okay, so I'm claiming that we can use S3 to move this triangle. Okay, to move this triangle. For example, what? Let's say 1, 2. Okay, what's your intuition here? When I say I want to move 1, 2, 1 to 2, 2 to 1, how do you move this triangle? Huh? How are you gonna perform the move here? Reflection. Reflection along where? So the perpendicular bisector of the edge connecting 1 and 2 and pass through 3. Okay, so let's try it. Okay, so you do a reflection here. Okay, so similarly you can do to 1, 2, 3, 1, 2, 3. Okay, let's do one more. Let's do one more. How about 1, 2, 3? 1 goes to 2, 2 goes to 3, 3 goes to 1. What happened to this triangle? Huh? Rotation. Okay, rotation by how many? How many degree? Sorry? 120 degree. So is it clockwise or anti-clockwise? Okay. Sorry. 1, 2, 2, 2, 2, 3, 3, 2, 1. Oh, sorry. Okay. So, so what's this? Clockwise or anti-clockwise? Clockwise and 200 degree. Okay, let's not write 120 degree. Not mathematical. 2 hours. Okay, thank you. Let's write pi professional. Okay, so you can do other permutation to see there's a rotation or reflection on this triangle. Okay，对不对？Yeah 没有，每次就看到这种东西，不是，可以想起来小时候玩的那种玩具啊。你小时候有玩玩具的吗？Did your parents buy you toy before, like when you are young? No, no toys. Then what you play家里？Then what you do when you are 1 year old, 2 years old? Start cooking Okay. Jump on the bed. Yeah. I remember my parents like to buy those Lego like highly symmetrical stuff for example the circle thing or triangle stuff then we will play around with it. Okay, then the shape still keep the same. So like how to say, I motivate the idea of symmetry. No matter how I turn it, no matter how I twist it, okay, it's still the same. Maybe I don't know anything about these word means, but the idea comes in first. Okay. Yeah. Idea is very important for mathematics. Idea. Idea 的中文是什么？概念。OK， 概念对数学很重要。我的导师曾经说过，我的毕业导师就说数学其实不是难。OK，mathematics is not difficult. It's just that you are not mature enough to accept it. 你还不够成熟。你看到那个 concept 的时候，你还不够成熟。有没有一个想法是有一个东西一直教你你就是不进脑的罢了。不管你会还是不会，你就是不进去，它就是不要进去这种感觉。你有吗？有这种感觉吗？学数学 有没有？我个人是有啊。就那时候不够成熟啊。比如说我学 epsilon delta 的时候，我第一年一进去学 epsilon delta，I don't know what is it。like 3年后，我走在一条路上，我才想起来，哦，I can understand, I can draw the epsilon delta 啊，3年后 ，OK，啊，我有没有 fail 掉？哦，it is a very interesting story 啊。Our mathematics first year is a mix of linear algebra and analysis, half half. So my linear algebra I get like 48 out of 50. Yeah, first year. But analysis, wow, first time I feel that I fail my maths, you know. I never fail my maths. You know what? It's like always 90, 100 my maths during high school. But it's the first time analysis made me feel like I failed my maths. I totally cannot understand the question. Yeah. I mean, I think I get about 10 or 20 marks out of 50. But in the end, still distinction because got assignment helping. I don't know. My assignment full marks on every time. Yeah. That's why I tell you assignment you can spend time, don't waste your mark. Yeah. So 子涵做得很好，其实你 assignment 挺好。Yeah. 考试不好不用紧，慢慢进步，可以慢慢进步。OK。assignment 一定要做好了，你不可能 fail。但是 free 的 mark 给你啊，48%，free 了，你肯定 pass 了。这样了。Yeah. All right. Another group action. Another group action. I think you have also seen it before. It's called a conjugation of complex number. Okay, actually, conjugation of complex number is a group action. What's a group? So what's the conjugation first? A plus bi will send to A minus bi. So we claim that this is the action of Z mod 2. Okay, or we write it as C2 lah. Okay, generated by 1 and minus 1. Okay, because if you're gonna conjugate again, what did you see? You get A plus bi back. So it's a order 2 action. Okay, it's an order 2 action. Okay, you do it again, you come back to the same thing. So this thing has a geometric way to understand, right? So for example, if you have A plus bi here, where's A minus bi? It's just reflect across the x-axis. Thank you. Okay, x-axis. Yeah, so although you just see conjugation in complex number, but actually it's a geometric operation. What time is it? Okay, let's define the group action and then we will take a break. Huh? 为什么？ Huh? OK， 好，不要怨气这么深吧。OK， 谢谢。OK, an action of a group G on a set X is a map. Actually, okay, it's a map. So when we say about group action, it is a map. Okay, group action will be acting on a set. So you have a group and a set with a map. Okay, so what's this map here? It's going from G cross X to S. So what's this map? I need to, given at a G, given an element in the set, I need to tell you it goes to which element in the set. Which element is it? You just take G composed with X. Okay. So I need to tell you what's this composition. This is not LOC, by the way, because the set might not be the group. If the set is a group, then maybe it's the same group, then you can use LOC there. Okay. But in principle, it's not, right? Because like what we did just now, 1, 2, 3, permuting triangle. Triangle is other thing, it's not number. Okay. Such that what? Few things you need to satisfy. So one thing is, for every element inside your set, what does the identity element does? It should keep your element. Okay, you don't move your S. Okay. Second, your group action should be associative. So what does associative means here? Please don't compose two set elements together. We don't know whether these set have composition or not. We can only compose G stuff together because we know there's a LOC on G. So where's the associative law here? So this was referring to the how products of group elements add on a set element. Okay, so this is equals to you first add your G prime on X first, and then you add G on it. Okay, so this makes sense here because once we have G prime on X, what do we get? We get another element in X. Then you can use G add on that element again. Okay, so this is a something in S. Obviously, in part 1 also S is in X. Okay. Okay. So to be convenient, maybe we don't put this star sometimes. Okay, sometimes we don't put star. Okay. Or sometimes we put dot also can. But just remember, this is not the usual LOC. You need to define it. Later, I'll show more example. Okay, any question before we take a break? So very important thing, two properties need to satisfy. One is about identity element, the other is about associative law here. Okay, because in principle, these two things might not be equal, but to fulfill a group action, they have to be equal. Okay. So this is a commutative diagram also. You compose first and then you add. It's the same as you add separately. Okay, so let's take a break until 6:02.
你们讲 S 这种 symmetric group 嘛，是你自己去 define 的嘛？所以
嗯
就好像我刚刚那个，我可以 define 1、2跟1、2、3，那你刚刚不是有 define 一个1、2、1、2、3？
132，
132好像是
对，
然后 generate 吗？像我是不是也可以 define 一个1、2、1、3？
那1、2、1、3也是 generate
啊，对吧？
你可以送去不一样的东西。
就我讲有一个 x 是1、2，y 是1、3，然后这样 x square 就是1，y square 也是1吧？所以然后我就可以讲什么 x等于 y。
要看你的 relation，要配对你的 relation。
为什么看到这个时候又看到一个很奇怪的说，如果我明明可以，就比如我就说我这个可以用我 show 的这个嘛，我就讲 x 是1、2，y 我 map x 是1、2，y map 去1、2、3，对，这样我就可以直接后面我就做到，对，我就想办法去写一写就可以了。然后但是我就把去1、2，x1去1、2，x2去1、3，然后我也可以想办法用他的方法去 map 正出后面这些东西。
OK。
这样我的问题是为什么我还要去修的这两个equal？明明修的 x3这个 S3这个我就已经修完。
那个是另外一条路啊。你是说 S3去两个东西，然后他们是等于 true S3。我这个是我 S3去这个先，然后这个去这个，
这可以
然后 S3才等于这个，
对，
都可以，这只是其中一条路吧。
哦
，OK。不一定要用我的题，怕有些人不知道怎样算。
哎，其实小群的那个 app 是不是要花题？
哪里？
表示自由群的那个 app 是不是要花题
？Script app 啊，Script app， 就是跟我那个形状有一个 script 是那个形状，我应该是 DF 吧，SRCF 我也忘记了。
没有，好像有一个 MAT 开头的。
MAT SCR 的。
哦，反正我下午找到了。
可以。哎，昊天呢？昊天不见掉了。
他不来上课，他也差不多。
我知道，只是他没有看到他考卷嘛。
啊？
他没看到他考卷。
他没来上课。
对呀、我就说，他没看到他考卷，
他 PD 已经确信75%了。
你就知道。你怎么知道？
领导上课有一天下课的时候在那边说我说这个人怎么学了那么多东西。然后林涛是自己在课前就说了，不到80%他也不会不让考试嘛，所以辽宁的再也不来。
OK。对吧？
很直观的一个例子是，矩阵作用在向量上面就是一个 group action。
哎，对，没有错，没错，
因为我听到这个的时候，第一个想到的是这玩意儿。
对，因为你们学 linear algebra。
对。
Hello。
你这里 C 是 C 吧
？B8比较正确，它 B 呀，从 B
这 B 也是可以
研
啊
究出来的，嗯，
，B 也可以，B 8也可以。
你懂的话就可以了。
但是他们两个不同 mapping 的，
对他们不同 mapping，但是 B8是从 B 出来的。
说 B 是直接 direct，B 8是从口子伸进去。
啊，对，
但是你 B 放口子进去也是可以。你 define on element 啊，就正确。
不是，如果 phi on 这个东西，你实际是看 phi on 这个 set，但是我们 phi8是把 cos 看成一粒东西，
对，所以
这是这个想法，yeah
那个是 bar。
yeah，其实没有大错，但是就是有这个两个差别。如果 bar 过后，你就把它看成一个东西，但是如果你用 phi，你把它看成一个 set，就是 phi of 这个 cos set 的 image。
还有，如果这个 free group 啊，它 isomorphic to 这个 quotient group 啊，就代表
它 isometric 有这个
如果
，OK， 如果是真的哈，这
它就
个是没有 relation 的，所以是说这里的 relation 全部都要 trivial，其实就要真的是 identity 在这个世界里面才可以。
你看啊，前面
Yeah，
你讲一个 G has a presentation if only has isomorphic to 自己的 quotient。
对，
所以如果我的 G 刚刚是 free group 的话，only has isomorphic to 它的。
对，但是 free group 没有 relation 嘛，所以这里面的东西其实本身就要是 identity 啊，不可以是 non-trivial 的东西。你就真的是切掉一群一吧，我那个等于一是因为切了过后才等于一，虽然我们有一点 abuse notation 说这里就等于一，这里就等于一，我们是有一点 abuse notation。
因为它的 E 有很多种形式啊，
什么意思？
就你的 E 来 Z mod 5，你的 E 有很多种啊，就你的08可以写成很多种啊。
是这个意思，不是这个意思，不是一个意思，不是这个意思。你刚才是说如果 free group 要 isomorphic to 这个 form， 对不对？你下面切的东西是真的是一来的，
真的是一，
真的是 identity，就是这些 word 是 identity。我们这样子写等于 identity 是有一点 abuse notation，是不是？
对，
我们有点
本来在这个 free group 里面，这些东西显然是不可能等于 identity 的，是我们在做了这个 quotient 以后，它才会等于 identity。
啊，
好吧，我上节课也没有怎么理解这个东西，现在我理解了。
哦，就是你要 set，就是 symbol 是没有意思的，没有意义的。
不是没有意义，是 symbol 它是做乘法的时候，
它
它不可能乘出 identity 来的。它做了这个 quotient 以后，其实它是在这个东西上面加一拔，会等于那个 identity 加一拔。
除非你直接拿
对，我觉得这样理解也不错。
除非你
然后我再重复一次。
除非你是直接拿这个 x symbol 的 inverse，它才会 cancel
啊，对对对对对对对对对对对对对对对对对对对对
只有在那个商群里面，
对对
它才等于 identity。
对对对对对对对。OK，我再
普通情况下是
我再强调一次，等一下，我再强调一次。
我 quotient 它的时候是代表它跟 S 已经有关系了。
关系这个词很玄乎，因为这边手也有关系，什么关系？ 我是切了过后，我要 show 它 isomorphic。
因为你这里的 relation 是从你 S3出来的，
可以这样理解，
什么？为什么这个
可以这样理解
人是出来是3出来的？
因为它 send 过去的时候，
这
在那
是你在做
个世界，
构造而已啊
在。那边是
这是
identity 吗？
只是你在做构造而已。实际上我们在从左往右推的时候，你应该怎么想？
没有，确实是他那个想法。其实如果你要找 relation，应该要去你的 image 那边看一下谁乘起来是 identity，、
OK
然后之前就要把它切掉了，
哦，
你
之前就要把它切。
后面那个丢一前面切它。
啊，你可以这样想，这 relation 可以是从后面想过来，后面呀，
那我其实刚刚在听的时候有一个问题，如果我把那个 yx 去掉，只是留前两个，它还是 x 啊？
肯定不是 isomorphic，
为什么？
因为你没有切掉那个就有那个就是 xy 跟 ys 跟 xy square 就是让它不 injective 好吗？
就我这样少一个条件，它是不是还是
不 injective，它不 injective，不
但还是
injective，还是有 map，
可是它
还是有 map，
subjective
还是有 suggestive， 但不 injective 啊。我要的是
可是
isomorphism，
你刚刚讲的不是 isomorphic 吗？
对呀、但是你讲把其中一个 relation 去掉嘛，
那所以其实你的那个箭头，它其实只有单向的，它没有双向。
哎呀，
那为什么你上个讲的是双向的
我后来是用 cardinality 的 argument 来 prove 的。
啊？
我是用前面有6个东西，后面有6个东西，然后那6个东西算去不同的6个东西，那个才是 isomorphic。
我知道啊，但是你上节课讲的时候，你就
哪一
claim
个？
了
上节课是哪一节课？
好像就是之前你讲这玩意儿的时候，你有一个 claim 是说这玩意儿是 一定 isomorphic 的。所以这个
是这个情况，不是说
哦，
只有这个特定的情况，
只有这个特定的情况。
啊
一般情况下，我们用这个定理的时候，它是不 isomorphic。OK，
我刚才有强调这个点，
可能我英语不太好，没有听清。
我就是讲它跟 first isomorphism 的差别就是这一个差别，
哦，我懂了。
差别还比较小。
差别就是这个
特别它比
phi
较小，
八
但是这个
就
phi 八它不一定是
isomorphism。
isomorphic，
如果这个 n 等于 kernel 才
是
是
isomorphic。
偏小
不，然的话就
如果小的话，它一定不是 isomorphic。你去想吧，我不想。
我觉得是。等一下先，但是我要点名先，我等一下要点名先。小杨，对，红杰，我等一下assignment交了吗？红姐，assignment 还没，赶紧交啊！子明，红姐这周交可以吗 ？OK，伟哲，没有点名，子航，曾子涵 ，OK，子航 assignment 什么时候交？啊？什么？现在交？没有哎，还没收到啊？你查一下，我这里没收到。曾子涵哦，assignment 4还没交。林晶 ，OK，Adrian，嘉玲，子轩，Lydia，Seng，嘉玲，赵琪，Eugene，Where's Eugene？Eugene 没有去家里，他累了，好，我也累了，我也去睡觉。Jasmine，Albert，陈碧，金鱼，OK，阿瑞，为什么你只好瑞？子豪，OK，戴一成，OK，心仪有在不是？九通有，冰箱呢？冰箱才能交，只是交，忘记交，赶紧交。小月，怎么今天没有在呢？小月没有在。子航、黄瑞、宇轩、佳怡、孙佳怡跟小月一起不在。王芳宇也不在。王佳怡 ，OK， 苏瑶、林思、苍云呢？苍云交了吗？苍云交了 ，OK。连胜有 Eric、钟一凡 ，OK。潘平、若星、赵胜、明春、昊天又没有来。金星、一涵又不在。修哲、Rachel、庞星、林恩、伊恩 Ian, you went to office hour on Tuesday, is it? Are you looking for me or you just try to get some help? Huh? You get help? Did you get help? A little bit? Okay. Are you finding me or not? Yes, because that day I'm a bit busy. So maybe next time if you want to find me, just come directly to me. Yeah. Okay. 正月 Sorry 呢？ Sorry 又睡觉啊？哎，拜二才看到他，拜二才看到他。哦，金鹏，刘金鹏没来。好 Hello, testing. Okay, so a little bit of reminder here. So I mean, when we write like this, this is a bit of abuse of notation. What do you mean by abuse of notation? If this thing really equals to E, your quotient by is just a trivial subgroup. Okay, so this is a bit of abuse of notation. But this is a usual way what group theory people did. So whenever they put this equal here, it says that they are equal to E after taking the quotient of this word. Okay. Does it make sense? After taking quotient only equals to E. Okay, this is a bit of abuse of notation here. 知道什么叫 abuse of notation 吗？知道什么是 abuse 吗？ Sorry ，sorry， 不要打你 ，sorry。OK，abuse 就是乱用，滥用，非常好，滥用。OK， 但是这是好的滥用。OK， 有分好坏。OK, abuse of notation here. So this is after taking quotient, because in principle, if you look at the free group, you look at yx, I mean it's just a normal word inside your free group. But why we put as a relation here is after taking the quotient, this word will become identity. Okay, after taking the quotient. Maybe this is not significant, but if I write it in this way, it would be better. For example, like this. Okay, usually in the maths literature, you will see this kind of thing. Okay, you won't see that something equals to E, but they will tell you what product is equal. Okay or not? Okay, because if it is a free group, 我们不会这样无聊 you know. If it is really just a free group, we won't put E here. 你懂什么意思吗？我们 abuse 是因为我们不会无聊到，如果它是个 free group， 我们放一大堆 E 在这边。You know what I'm saying? If it's just a free group, if it's just a free group of n elements, we won't put any relation here. Okay, so if we're gonna put relation here, meaning we're gonna quotient out something else. 你明白吗？我们不会无聊到，如果是个 free group， 我们放一大堆 E 在 relation. It's useless. Okay, so whenever we put something here, we mean we want to quotient out that word. Okay. For example, if I write these two relations, what's the word I need to quotient out? I test you. Huh? What's the word we need to quotient out? Xj, xi, inverse, sj, inverse. So this is the thing you need to quotient out. How about the next one? xi, xij, xi, xi plus 1 inverse, xi inverse, xi plus 1 inverse. Okay. But 你就会问咯，哎呦，怎么不要这样写，要这样写 ？Because you will know in your assignment paper. You need to use this for calculation wise. 你看这样多 inverse 丑吧，很丑，很丑。Okay, but we can make one product to something else if I write like this. 可以吗？虽然是一样，但是用途不同。Okay, so algebra 我们 as an algebraic person, we are very sensitive to this kind of presentation. Okay, different presentation will be of different use. Okay or not? Yeah. So in the next assignment, you will play around. Is it next assignment? 看下 next assignment 什么题目啊？ See? There should be another question, or maybe the next assignment. Yeah, this is about group action. Or I go back check first. Maybe put at the next assignment. Okay. Okay, so let's continue. Okay, let's give more example on group action. So what sort of group we see before? So for example, the very familiar group to you is the SN. Okay, SNX on what set? 很多人在读那个考卷的时候读不明白的 symmetric group of 什么 S4 S4 of 4 and 4 indexes 什么意思啊 How do we define symmetric group? Permuting n indexes. So Sn actually has an action on n indexes, set of n indexes. Why I say like this? Why do I say like this? I mean, if you put, for example, a cycle here, I mean, let's fix a further example. Let's take n equals to 4. Okay, so x4 is adding 1, 2, 3, 4. So what does group action have to tell you? It is a map. So what's this map? Called row S4 cross G. Okay, so let's call this is G to G. Okay. How to define it? So you need to tell me all the possible S4. Okay, how they gonna add on all the element in G. For example, in this case here, 1, 2 add on 1 should go away. Should go where? What do you think? 1, 2 add on 1. Yeah. So this is the natural thing we did before, right? 1, 2 sends 1 to 2, 2 to 1. Correct or not? So you see on every element of S4, you need to tell me how it acts on everything in G. Okay. Obviously, you need to define for other elements like 1, 2, 3, 4, how it acts on other things, right? Well, I mean, you also need to check how act 1, 2 acts on 3 and 4, right? What they do there fixes 3 and 4. Okay. 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 So what can you see here? Okay. So you can see that this group action is actually a way to encode how these encode how the elements in Sn add on n indexes. 对吗？你放不同的可能性进来。Okay, you check on every group elements on every n indexes. Okay, how they add. It's a one way to put all things together. Is it associative or not? Is it associative? Okay, so what does associative means? For example, if you have 1, 2, 1, 3 add on 1, okay, is this the same as you first do 1, 2 on 1 first, and then you do 1, 3 on it? Okay, is it the same? Okay, on the other side, it's non-trivial because 1, 3, I mean 1, 3 times 1, 2, what do you get? You get 1, 2, 3. Okay, so are they the same or not? Do they same to the same place or not? They same to the same place. 1 go to 2 and then fixes 2, and then the other side 1 sends to 2. You see how it's non-trivial, you know? It's non-trivial, right? So first you send 1 to 2 here and then fixes 2, but here you directly send 1 to 2 only. Okay, it's non-trivial checking actually. Okay, so you really need to check whether map from G cross X to X that you define is a group action. That is non-trivial to check. Okay. What else? Okay, just now, Eric give a very good example, your LA example. What's your LA example here? GLN can X on. I haven't introduced this notation 啊，没有人问我的，没有人问我这个画圈圈是什么咩？啊 ，X on， 哇，这样聪明，我靠，难怪你们，我看得起你们哦，原来你这样聪明。原来你这样聪明。Okay, sorry, I forget to tell you how to draw this group action here. So if we have a group action, we will write G, a circle on X. Okay, G and on X. And then there's a name for this set. This set come with a group action of G. We'll call it a G set. We'll call it a G set. So we'll say that this set have an action of G. Then we call it G set. Okay. Yeah, so just two pieces of notation. Okay. Okay. So GIN X on what? X on n times 1 vectors. Okay. GIN X on n times 1 vectors. 对吧？对还是不对？ If you take a matrices, you multiply. Let's take a identity. Multiply a vector. Okay, let's say A1 up to AN. Do you get a vector or not? Right, you get another vector. So in this case here, I also prove to you that if you take an identity element inside GRN, you add on the vector, you get back the vector yourself. Okay, so first law satisfied. Second law, second law says what? If you multiply two matrix together, and then you add on a vector, let's call it P hat. Is it equals to V on V first, and then multiply by A? Go back and check your LA textbook. You should have this. Okay. If not, ask Ali to prove it. Okay. Yeah, you should know this. This is how you computed actually, right? You use without thinking. You think 吗？算的时候以前有没有 think？ 有没有想过可以先把前面两个乘起来，再乘 vector 和分开乘是一样的？来过吗？ If not, you should go and try your LA exercise. They should be the same. Okay, and then you should prove it they are the same. How to prove it? You just use term by terms, or like how we did for the associative law in matrices. Okay, in this case here, actually V times 1 is also a matrix, right? Right. So this is the size of n times 1 matrix. Okay. So it's a similar way to prove it. Okay, so I mean exercise, try and prove it. In general. Right. Okay, so let's continue. For definition. Given an action G on X. For all G in G, we'll define a map called the left multiplication, which is MG. Okay, so this is the left multiplication by G. So what is this? So this defines a map from S to S, okay, which is X going to GX. This is what we call a permutation, or some book will call it operation. Okay. And then if you look at the image, where the images of this map will constitute the permutation set, okay, which we call a perm X, permutation X. If you let me think. Okay, yeah. So does this look familiar? Yeah, we use this construction to prove the Kelly's theorem here. Okay, so now we're gonna play with a more general setting. Yeah, more general setting here. So why is the permutation here? Because what? If you want to prove that this is a permutation, you need to show that this map is bijective. Is it bijective? What's the inverse? How to go backward? G inverse. Okay, just multiply G inverse. Okay. Okay. Right, so this is the left. Okay, so let's make a remark here. We're gonna show you very advanced stuff now. So this, the collection perm X, okay, the collection perm X will form something called the representation of G. Okay, so we are touching a bit of representation theory here. Representation of G. So let's highlight it. This is a name. And when a set is the group itself, this is what the Kelly theorem proved using. So this is called the left regular representation. Okay, so whenever we say regular representation, we will means that the group add on itself. The set we take is itself. Okay, regular 普通的自己可以对自己作用吗？ Correct 吗？ You know how to multiply to yourself. How to multiply to yourself? You just take the normal LOC. Okay, if it's different set, then I need to tell you how it play around with the set. If it's your itself, your group, then you just do the normal LOC. Okay, so this is the one that we define in, I forget what's the lecture already. In the lecture, having the proof of Kelly's theorem. Having the proof of Kelly's theorem. 哪一个字？上面是哪一个？去 constitute 啊 ，constitute。constitution 知道是什么吗？宪法。为什么 constitution 是宪法？因为它是组成这个国家最重要的一个东西。对啊 ，constitution。OK， 没有宪法，你这个国家就不存在。哎，你要有一个国家，你要有宪法先，知道吗？要有一套规则先。所以为什么国会要修宪法这么重要 ？OK， 宪法一换，你这个国家就换了。看到，法律不可以高过宪法。Okay, law cannot go above constitution. Okay, law must abide to constitution. 知道吗 ？You know this? 如果这个 law violates constitution, then this law is ineffective. OK， 哎，你没有读过是不是 MPU？ 有没有读 MPU？ 有没有？哦，换了哈。OK。Okay, so let's continue. Definition again. So let's define a group. So given a group action, we can look at something called the orbit. Okay, so what's orbit to you? Like orbit of sun, right? Where it moves. Okay, so this is the same. So we'll define an orbit for an element in X. I want to see how the elements in X move. Move based on what? Okay, moves based on what? So it is all the element x prime x such that x prime equals to gx for some g in G. So meaning if you fix, so let's draw a set here, x. Okay, and then you have a group G, something like that. And then you just pick one x out of it. So pick one x here. Maybe you have G1, G2, G3, G4. Okay, you want to see where this x go after you add by G1, G2, G3, and okay, maybe I draw a bit larger here. So let's look at a small s here, and then let's say we have a group. Let's say 4 of them, G1, G2, G3, G4. We want to see how this x, and after you add by G1, G2, G3, G4. Okay, so maybe you have G1x, G2x, G3x, and G4x. Okay, so you take all of them together. They will form a orbit. 哪个符号在哪里 ？Which 符号 ？Which 符号 ？Orbit 哈 ，the script all is a script all. Yeah, script all. 怎样写？就是漏风的哦。漏风啊，本来 all 要这样嘛，它漏风了。可能画的有点丑吧。something like this 啊，它不远了。topology 嘛。topologically is the same. topologically 的，有吗？呀，全部人看一下，差不多了。看到了，看你，不是很像吗？可是那个刘海比较长一点嘛。Okay, so for example, so let's look at example. Let's look at example. Sn add on 1, 2, 3, right? So let's ask you, what's the orbit of 1? Where 1 can go? 1, you use identity. 1 can go to 2 or not? How to go? Add by 1, 2. No. 1, 2 add by 1 is 1, 2, right? 1. If I take 1, 2, add on 1, I get 2, right? Okay, what's the other thing inside my orbit of 1? Is 3 inside the orbit or not? How? 1, 3, good. 4, 1, 4. So you can deduce that actually the orbit of 1 is everything from 1 to n. You just use 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, n. Okay. So meaning this orbit is the set itself. Okay, it's the set itself. How about O2? The orbit of 2. Who is inside there? Is 1 inside there or not? Why? Because you take 2, 1 on 2, you will get 1. Similarly, you will get all the other elements inside here. Okay, so basically, OB of 1 is equals to OB of 2 equals to OB of 3 equals to OB of ON for ON, N for ON, N for ON, K for ON. Okay, thank you. Thank you. 很好，非常好，很开心啊！有人学会了是很开心的一件事情。因为如果一看到这种东西在我 project， 我就头很痛。我不会，我头很痛。OK。Okay. Proposition. The orbits for a group action again will form a equivalent classes. There's a new way to partition your set. Okay, this is a way to partition your set. So I form equivalent classes. So whenever you see equivalent classes, you need to ask yourself, what equivalence relation is it? Okay. So it is a theorem says that if you have an equivalent classes, you will have an equivalence relation. If you have an equivalent relation, you will have an equivalent classes. So it's if and only if. Okay, so what's the equivalent classes here? I will tell you by telling you the equivalence relation here. Two set elements is equal if there is a group element that send one to the another. Okay, send one to the another. Note that this one is invertible. If you know that I can go from S to S prime, you also can go from S prime to S. How? Yeah, take G inverse. But this is not from cancellation law. Not from cancellation law, you know. Because this is from different places. How do you prove that? How do you prove that? How do you prove that G bar inverse S prime is equal to S? How to prove it? This is no cancellation law. No cancellation law exists here because S is from S, a set, G is from group. No cancellation law. You only can use group action to prove it. How to use group action to prove it? So the claim is this. So why? No cancellation law because it's not all of them group element. You only can use group action definition. Let you think 1 minute. You can say if you got idea. Because this is a very important skill to play around with group action. This will show the significance of the two things that we define in a group action. Any idea? Yeah. 想一想，问问同学也可以。Any idea? So these two things is in S already, not G anymore. No group element inside these two equations. This one equation, I mean. Because after G add on X is something in X already. 是一个在 set 里面的东西。So in the example of Sn, 它们就是两个数字罢了。So how you introduce the G inverse here? What to do? You apply G inverse on both sides because they are the same element, right? So if you do a G inverse action on both sides, you should get same thing. But the key point comes here. The key point comes here is on the right hand side. What do you need to show to the right hand side? Have to be equal to S. But how do you combine G inverse and G? By group action, this is associative. So you can first compose the group element together first. Then this is a operation in group, LOC in group. What do you get? You get identity. But what is identity on X? By identity law. You see, I use all the axiom from group action. Okay, so this one is a. Okay, so let me specify here. Here is associative law. And the second one is identity law. And so I've made full use of the definition of group action. Okay, so it's really important that two condition there. Okay, yeah. So I make a remark here. no cancellation law because it's not a no cancellation law because it is just set. Because it's just a set. Because they just live in a set. Okay, because they don't okay that live. Okay. Right. Well, I mean, from this proposition, a corollary is this orbit will partition the set. Okay. So you see, we have a group action. We have a group action G. Okay, we have a set X. Set X. Okay. So set X has a partition. How to form the partition? You will use OX. Okay, maybe OX or G1X. Sorry, shouldn't be OG1X. Maybe OX1, OX2, OX3, OX4. Okay. On G side, you also know how to partition, right? Maybe you have a subgroup. Okay, maybe H, GH, G1H, G2H, G3H. Okay, so maybe you can see how they interact. Okay, in future. Okay, in future. Okay. Definition again. So we'll define that a group action. 嘉玲这么好像上好像局外人这样。It's called transitive if there's only one orbit. Okay, so what this means, so for example, just now we show that when xn add on 1, 2, up to n, the indexes, what's the orbit of 1 and 2 and 3? They are all equal. Okay, they are all equal, and then they're equal to the set itself. Okay, let's call it x. In this case, we'll say that xn add on n indexes transitively. Maybe you will ask a question here, and you just talk about OX. How about OX? Maybe OX2, OX3, OX4, OX5. But the problem here is this is meaningless. 不用问的。啊，这么忽然间 Eric 哦，来解释一下。
因为它的这些 O， 我就叫 O1、O2、O3，它是一个 equivalence class， 然后既然一个东西它已经是整个东西了，那其他的东西，因为 equivalence class 之间肯定是 disjoint 嘛，它也没有其他东西跟它 disjoint， 可能是它必须是同一个东西。
Yeah, so meaning what? If I say that O1 is already everything, if you ask about O of another thing, should be living inside the same OX. And so it's we not only need to talk about one OX. Because all the other things should live inside there. Because why? Because this single orbit here is everything already. Connect everything. So if you ask about other thing, 恒星住哪里? Okay, sorry. So let's say this class. Let's say this class is one orbit. Let's say this class is one orbit. Okay, it's one orbit. Okay, one orbit. Maybe orbit of Rosing. Okay, so all of you live in the orbit of Rosing. Then 你还问恒星在哪里吗? No need to ask already because all of 恒星 is equal to all of Rosing. Okay, so nothing to talk about. Okay, yeah. Maybe 我画一个图给你看，可能你们会比较开心一点嘛。我画一个图给你们看。来，我画一个图给你们看。So this is x1. So let's do S5, okay? Let's do S5. So there's an action of X5. I think of it. Right? So what's the orbit of 1 here? Okay? So you can go from 1 to 2. 1 to 3, 1 to 4, 1 to 5. Okay, so when I say O1 equals to O2 means what? So O1 is everything, meaning I can go from 1 to everything else. But if this happens, meaning 2 can also go to everything else. Do you know how to go? Just using the same way, same arrow here. Go backward, no? Why can go backward? Why can you go backward? Why can you go backward? 很重要这个问题。Why can you go backward? Why can you go backward? Huh? Why can you go backward? Backward means what? Backwards means what? 1, 2 times 1 equals to 2. Backward means what? Something times 2 equals to 1. What's the thing you need to take here? Inverse, no? Okay or not? So why the arrow can go backward? Because you are taking group action. Group element is invertible. So you can go backward. So 2 how to go the other way. So 2 can go like this. 2 go how to go to 3? Can go like this. Okay, and then how to go to 4? Go like this. Go like this. Okay, so this is the one way to go. But just now you give me the other way, right? 2 can directly go to 3 also. 2 can directly go to 4 also. How? Just take the transposition 2n, okay, or 2i. Yeah, no? Okay. Yeah. Does it make sense? Okay. Okay, another thing is about stabilizer. Okay, so there's a bunch of definition today. So stabilize means what? Stabilize means what? Stabilize. 稳定. Okay, 看一下怎么稳定啊。So this is a stabilizer of an element. S also. Okay, orbit we define on X. Stabilizer also defined on X. But in this time, this is a set of group element. Okay, so stabilizer is a group element. 因为为什么你要稳定的话，你自己是稳定不了的。如果你是个精神病人，你是稳定不了你自己的，你一定要靠别人来稳定你。So here stabilizer of X is a group element that stabilize these set elements. OK， 你是稳定不了你自己的，你一定要别人来，either你吃药，或者有人帮助你。OK， 因为你已经有精神病了，你就是控制不了自己，你才有精神病。OK， 你已经 stabilize 不了你自己了，所以你才有精神病。OK，so it's a set of group elements that leave X fixed. Okay, so meaning what? So what is Gx here? So Gx here is everything in G such that Gx is equal to S. Okay. Okay, so what is OX 啊？来考一下，5分钟就来考试了。OX, what is OX? Everything in S such that there exists a group element that sends S to S prime. Okay. Can you see a difference or not? One is a subset of X, the other is a subset of G. Okay, so 不要混啊，不要搞乱啊。Okay. Okay. So 你看啊，你看我们，no， 哦 ，sorry，sorry 啊，太紧张了。Okay. So right. So we have a subset of G here. 我们每当看到 subset of a group 啊，我们想干嘛？不知道，不知道。上完今天课你一定要知道，每当我们看到 subset of G， 我们就想问一问它是不是个 subgroup。对，所以我们现在就要问它是不是一个 subgroup。We're going to prove that GX form a subgroup. Forms a subgroup. Okay, form a subgroup. 自己回家证。哦，干嘛要一起证啊？要一起证？要啊。OK，温习一下 subgroup 的 property 啊。什么啊 ？Closure、identity、inverse，哎，应该是有一个最简单的吧？引起公愤。OK，哪一个最简单？Which one is the easiest one? Identity, correct, right? Right, because it's directly coming from the group action axiom. Okay, one should send x to x. Closure, if g prime, if g1 x equals to x, g2 x also equal to x, then g1, g2 x should be equals to s. Why? Because we can write g1, g2s as g1, g2 on x first, and then apply g1 by associative law. But g2 is s. g1 on x is again s. Okay, inverse it. If g1x equals to x, then yg inverse x equal to x. I think this one we did it just now, right? Yeah, just now we did it. Still remember how to prove it? How to prove it? G1 inverse on G1 S equals to G1 inverse X. But you use associative law to see that G1 inverse composed with G1 is just identity, which is just, okay, yeah. Okay, now. Okay, yeah. Right. Bless you. Okay, so look at one example here. So again, we use S and add on the 1, 2, 3 to n. So let me ask you, what's the stabilizer of 1? What permutation fix 1? Huh? 没有1什么？没有1的 cycle. Okay, so this one. Cycle not having the index 1. For example, what? I give some example. I just mean, what sort of cycle doesn't contain 1? 2, 3, good, very good. Okay, maybe we can have product of disjoint cycle, right? Okay, cycles or product of disjoint cycles, or we just say product of disjoint cycles. We make cycles into disjoint cycles. Can we give an example of product of disjoint cycles, non-trivial one that doesn't have 1? 2, 3, 4, 5. Okay, yeah. Okay, yeah. Okay, very good. Right, yeah. So actually, these subgroup, right? So let me put here. Actually, so it form a subgroup, right? So you want to ask what's the subgroup? What's this subgroup inside Sn here? It turns out that it is there's a very nice description of this subgroup. Okay, so this is subgroup of Sn minus 1. But this n minus 1 here is a bit special. It's just permuting 2, 3 up to n. Okay. Okay, no. Does it make sense? Okay, so let's put a prime here, not to confuse you. 白吗 ？Any question about this? You. Okay, I mean, we can stop here. Any question? Any question? 明白这是什么意思吗？明白吗？OK。哦。Okay, yeah, if no question, then we will finish. See you next week.
那我觉得你刚刚有个东西定义的有点怪怪的。